All right, let's talk about tangent planes. I think big takeaway here is that a tangent plane is to a surface at a point as a tangent line is to a curve at a point. And finding tangent planes uh, for our purposes really is reinforcing some of the ideas that we've learned earlier as a sort of a theoretical application of some of the ideas that we've learned earlier, and a nominal sort of practical application is that it is the case that tangent planes are used to approximate functions near a point, especially, for example, in computational problems where calculating the function values is expensive, but calculating the values of plane functions is easy, and so computer scientists might use this technique to make their code more efficient in certain circumstances. Our goals are to determine the equation of the tangent plane to a surface at a given point, and I am going to sort of talk briefly about the derivation of the formula for this plane that's given in the textbook, and then I'm going to go carefully through an alternative derivation that I think sort of shows or applies more of what you've learned so far in this semester and maybe is a nice review of some of those ideas. And then just as a side note, some of the exercises that we'll do will recall the idea of implicit differentiation briefly. So two ideas that are not well covered in this particular section but are important to the class and I will be emphasizing as we discuss. Okay, as I mentioned already, the big idea narrative, tangent planes are like tangent lines. The derivation of the tangent plane formula is a reinforcement of space curves, cross products, planes, the one that I'm going to give you anyway, not the one that is in the textbook. And the tangent plane can be used to approximate a surface near the point of tangency. I want you to pay attention in particular to example 4.23 and checkpoint 4.20. We're not going to do this whole section. We're going to stop at the differentiability section, and we're not including that section or any of the topics afterwards. Okay, let's begin the flyover. So tangent planes, here's a nice picture. We can't really rotate this figure, but we imagine this surface and this point on the surface, and we're finding this tangent plane that just touches the surface at this point. You know, there are lots of surfaces that might just touch the surface at a point. This one is special because it's tangent to curves that go through this point. So any curve that goes through on the surface that goes through this point will have a tangent vector that's parallel to this plane. That's what makes it special. We can see that in the definition. If we let P be a point on the surface S and C be any curve passing through that point lying in S, then the tangent lines to all of those curves at P0 lie in the same plane, and I think it's probably safer to say, well, no, the tangent lines do. The tangent vectors to those curves are parallel to the tangent planes. The formula for tangent planes is intimately related to partial derivatives, and that's one of the reasons we are now talking about them, because we have the ability to do partial derivatives. The tangent plane is given by this expression, where if you pick a fixed x0, y0 value in the domain of f, that's going to define a point on the surface, x0, y0, and then what you get by plugging in x0 and y0 to f. And that point's going to sit on the surface, and it's going to sit on the tangent plane. And the formula for the tangent plane is this, and we can see that it's a plane because this is a constant, this is a constant. Everything is constant except for z, x, and y. These are the independent variables. And they all appear linearly. And we know that in 3 dimensions, if we have an equation where all of the independent variables occur linearly, then we have a plane. This particular plane with these particular coefficients is going to be tangent to the surface at the point x0, y0 in the domain. Where does this formula come from? Well, the book sort of jumps a little bit in a way that I think is not valuable. The book immediately jumps to the fact that the equation of the tangent line to the curve that is represented by the intersection of S with the vertical trace is given by this expression, z equals f of x naught y naught plus f sub y x naught y naught y minus y naught. You know, if you want to take that at face value, great. Then we can quickly find the tangent vectors to these traces, and we can get a tangent vector in the direction of the y trace and a tangent vector in the direction of the x trace. We can compute the cross product of those two tangent vectors, and what we get is a vector that's perpendicular to those two tangent vectors, and consequently that vector is perpendicular to the surface at that point. And what do we need to define a plane? We need a vector, a normal vector, and we need a point on the plane. And that normal vector that we get as a result of this cross product is precisely the normal vector that we want for the tangent plane. And the point is precisely the point that we want for the tangent plane. We put those together in what we already know about equations of planes from earlier sections, and we immediately arrive at this formula. I'm going to go into this idea a little bit more in depth in our notes. So let's talk a little bit about that. Give myself some space here. So we've talked about the book's version. Let's talk about my version. All right, in my version, again, the problem that we're faced with is we want to find the tangent plane of the surface z equals f of x and y, because surfaces can always be written like that. Z equals f of x and y at the point x naught, y naught in the domain of f. So it's important to note here that the tangent plane is not going to be tangent to the surface at x naught, y naught, because that's not where x naught, y naught lives. X naught, y naught lives in the domain of f. It'll be tangent at the point, using the book's notation for point, capital P, at x naught, y naught, and then what's the z coordinate of the point of tangency? It's the value that I get by plugging x naught and y naught into f. So f of x naught and y naught, like that. Okay, great. So we're going to find this formula, and what we're going to do is find the space curves that represent the traces that go through this point on the surface. So we want to find space curves on the surface through the point P in the x and y directions. And you have to be careful with the notation here. Remember that we always use space curves as r of t, right? T value moves us back and forth along the space curve. I'm going to say r sub x is the space curve in the x direction, and we can write that in vector form as if we're moving in the x direction, then the parameter t is going to be in the x coordinate. We want to make sure that we pass through x naught, y naught, so we're going to put y naught in for the y coordinate, and then what's the z coordinate going to be? It's going to be f of t, y naught. All right, so this curve sits on the surface and it moves back and forth with a fixed y value, so it's parallel to the x-axis. And similarly, we'll define r sub y of t to be x naught t f of x naught t. And this curve will pass through the point P so this hits P when t is equal to x naught, and this one hits P when t is equal to y naught. So these are two different space curves. Now remember that we can get our hands on tangent vectors to space curves by differentiating the space curve with respect to the parameter t. So let's find the tangent vector for r sub x. And you know what? I don't want to call this capital T because that's the unit tangent vector. So let's just call it tangent vectors for r sub x. We do that by computing r prime. And r prime is just the derivative with respect to t, the parameter. Well, the derivative in the first coordinate with respect to t is just 1. In the second coordinate with respect to t is 0 because that's a constant. And in the third coordinate, let's be careful here, this is the derivative of this function with respect to t. So that's the partial of f with respect to x because we're in the x coordinate as a function of t. So this is tangent. And similarly, for r sub y, we can compute r sub prime as 0, 1, f sub y, x naught, t. This is tangent. The first one is tangent in the x direction along the curve, along the surface. The second one is tangent along the y direction. If we want a normal vector, oops, at x naught, y naught, let's first get the tangent vectors at x naught, y naught. The tangent vector in the x direction, let's call it, I don't know, I'm going to call it capital T sub x just because it's begging to be called that, is going to be 1, 0, f sub x of x naught, y naught. And the tangent vector in the y direction at the point x naught, y naught is going to be 0, 1, f sub y, x naught, y naught, like that. Okay, if I want the normal vector or a normal vector at this point, I've got two tangent vectors. I'm just going to compute the cross product and we'll get a normal vector. All right, let's do the normal vector. In the first coordinate, we're going to blot out the first column and do the little determinant in the second two columns. So we get minus f sub x, x naught, y naught. In the middle column, we plot out the middle column. We get f sub y, but there's a minus sign because we're doing cross product. And then finally, in the last column, we blot out the column with the f's, and we get 1. So a normal vector at P is given by this expression. Well, now we know a normal vector, and we know a point on the surface. Given a normal vector and a point on the plane, we can very quickly write the equation of the plane. You can go back and look at this in the earlier section about planes. It's simply the dot product of x minus x naught, y minus y naught, z minus, we don't have a z naught, but we do have f of x naught, y naught. We want the dot product of that vector with the normal vector minus f sub x, x naught, y naught, minus f sub y, x naught, y naught, 1. We want that to equal 0. And if you do the dot product and you solve for z, you get exactly the expression that's in the textbook. Like that. That's the equation of the tangent plane. All right, so that's a derivation that I want you to read through and understand. I want you to be able to talk about these kinds of ideas. So we're taking what we know about space curves and their derivatives, and we're now using them to calculate normal vectors. I have a quick little GeoGebra visualization of this situation. Let me grab that for you. This is going to be in 3D, so we'll start the 3D calculator and let's open up this visualization. All right. So this is an example that we're going to see later in the lecture. We're using a specific function now, 1/2 natural log of x squared plus y squared. That's this purplish surface that has the singularity at the origin, goes to minus infinity at the origin. And remember that the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. So this black line here is the trace in the x direction. This black line is the trace in the y direction. And I can move that point. So I'm interested in the tangent plane at the point A. So if you look at the point A here, you can see that it sits on the surface. Furthermore, you can see that the trace passes through, the trace in the x direction passes through this point A, and the trace in the y direction passes through this point A. And if you look closely at this, you can see the tangent vector in the x direction is parallel to the tangent plane. And the tangent vector in the y direction is also parallel to the tangent plane. And when we take those two tangent vectors, one pointing in this direction, one pointing in this direction, we compute the cross product. What we get is the normal vector to this light blue tangent plane at the point A. And combine that with the fact that this plane has to pass through the point A, we get a really quick way of calculating the tangent plane at the point A. So that's what's going on here, and the mathematics is over in your notes. And I've written this generally so that I can move x naught and y naught around, and if you change x naught, the point of tangency, you can see the plane shifting around beneath it, the tangent plane kind of moving around beneath it. And if I move y around, again, the tangent plane kind of moving around beneath it. But it's always the case that the tangent in the x direction along a trace crossed with the tangent in the y direction along the trace is the normal vector to the tangent plane. Really important idea. All right, we'll come back to this example in a bit. Just to reinforce this idea, let's go back to the textbook and look at example 4.22. So we're given another surface that's sine of 2x cosine of 3y, and we want to find the tangent plane at the point in the domain pi over 3, pi over 4. Let's just walk through the solution here. In order to build a tangent plane, we of course need the partial derivatives. So we compute the partial derivatives, and then we evaluate those partial derivatives at the point of tangency, pi over 3 pi over 4. Again, this point of tangency, it's not really the point of tangency, it's a point in the domain of the function f where we want to build the tangent plane. So if we want to find the z value, we have to plug in this point in the domain and compute f of pi over 3, pi over 4. So this gives us the z value. The 3 points together give us the point on the plane. Once we have these components, it's a matter of just dropping them into the formula for the tangent plane. So we've computed f of x naught y naught here. We put it in. We've computed the partial of f with respect to x at this point here, and the partial of f with respect to y at this point here, and then x minus pi over 3, y minus pi over 4, and we're done. That's the tangent plane. Simple as that. So applying the formula is relatively straightforward, and you can just memorize the formula. Deriving the formula, which I think is also useful and helps with your understanding of lots of these concepts that we've covered over the last couple of weeks, I think is more important in a lot of ways and reinforces these ideas. All right, let's continue the flyover. We'll finish up with this idea of linear approximations. The tangent plane is a linear object, and because it's close to the surface at the point of tangency here, if you look at this, it's very close to the surface near this point of tangency A. The values, the z values on the surface are close to the z values on the plane. So we can use the plane as a simpler representation, an approximate representation of the surface values near the point A. This is akin to approximating a complicated function, like this function in blue, by a linear function, this function in orange. And we've learned from calculus how to do that from Calc 1. Here we see the Calc 3 version of a linear approximation at a point, and if you look closely at this, the right-hand side is exactly just the tangent plane at the point x naught, y naught. All right, continuing, we can use the tangent plane approximation. You can look at this example on your own. I'm going to do an example in the notes. And here we reach the end of the material that I'm interested in you learning for this section. So stop here and ignore everything below differentiability. There's a lot here, but for the sake of time, for the sake of getting through this semester in a timely way, we're going to de-emphasize these ideas. It's not that they're not important, but they're just not as important as some of the other things that we want to get to. Let's look at some of the exercises at the end of the section. In exercise 164, we'll start off relatively easily. We want to find the unit normal vector to the surface at the indicated point. Finding the unit normal vector is a lot like finding the normal vector to a plane. If you can write the tangent plane, then you can pick off the normal vector in the way that we used to back when we learned about planes. How do you find the normal vector to a plane? You just pick off the coefficients of x, y, and z, put them in a vector. That's a vector that's normal to the plane. If it's normal to the tangent plane, it's going to be normal to the surface. Let's look at this surface in 164. This is not a wonderful example, but we'll work it anyway. The natural log of x over y minus z equals 0 can actually be simplified dramatically. If we raise both sides to the e, to base e, what we get is x over y minus z equals 0, right? And if you multiply both sides by, I'm sorry, not 0, 1, e to the 0 is 1. If you multiply both sides by y minus z, you get x equals y minus z. And what we've discovered is this perhaps complicated looking expression for some surface is actually just a plane. And we can put it in standard form, x minus y plus z equals 0. This is a plane. And the normal vector is just pick off the coefficients, 1, minus 1, 1. So that's normal to this plane. And in fact, since the whole surface is just a plane, this vector is normal to the entire surface. Just a quick review, I guess, of finding normal vectors to planes. Okay, also by way of review, we're asked to find a normal vector and a tangent vector at the point P. All right, let's look at 168. What are we looking at here? This is actually a curve in 2 dimensions. So we're still kind of reviewing things. The challenging part about this curve is that it's not of the form y equals some function of x. We see that x is sort of buried in here in lots of different ways, and y is sort of buried in here in lots of different ways. And you might think, well, how am I supposed to figure out this tangent vector? One way to go would be to actually compute the slope of this curve at the point 1, negative 2. But since you can't solve for y as a function of x here, at least not easily, you might think, oh, that's really hard. I can't compute y prime. But don't forget about Calc 1 when you did implicit differentiation, where we pretended or assumed that y is a function of x. And I'll use this kind of weird notation, just as a reminder that y is a function of x. This is me mathematically declaring that y is the dependent variable and x is the independent variable. And remember that we always differentiate with respect to independent variables. We never differentiate with respect to dependent variables. So we can differentiate this expression with respect to x implicitly with respect to x. All right, so we have the derivative of the first term with respect to x is going to be, oops, perils of being left-handed, 6x squared minus, now we've got x squared times y squared, and these are both functions of x because over here we assume that y was also a function of x. So that means we have to apply the product rule. So I'm just reminding you about implicit differentiation. So that's x squared times the derivative of, so it's the first times the derivative of the second. So that's 2y dy dx plus the second times the derivative of the first, 2xy squared. And on the right-hand side, we have the derivative with respect to x, that's 3 minus dy dx. And the derivative of the constant 7 with respect to x is 0. There's no need to really clean this up. At this point, just substitute the point 1, or substitute the point 1, negative 2, x equals 1, y equals negative 2 into the expression. So we get 6 times 1 squared minus the quantity 1 squared times 2 times, what's y, negative 2. The unknown is dy dx, that's what we're trying to figure out, plus 2 times, what's x, 1 times y squared, that's going to be, well, let's just put negative 2 squared in there. All right, all of that looks good, equals 3 minus dy dx. All right, let's evaluate some of these expressions. We have a 6, we have what, minus 1, 1 times 2 times negative 2 is negative 4, so we get plus 4 dy dx. So that takes care of all of that. And then we have 2 times negative 2 squared, that's going to be what, 8? So negative 8, like that. equals 3 minus dy dx, like that. All right, let's move the dy dx on the right over to the left. And let's move the 6 and the -8 over to the right to join forces with the 3. That's going to give me a 5. And we've learned that dy dx is equal to 1. How does this help me answer the question? In particular, how does this help me figure out what the tangent and normal vectors are? Well, what I've learned is that along this little stretch of curve, whatever this strange curve looks like, along this particular stretch, I know that it looks like this. It has slope 1. Slope is 1. That's what dy dx is telling me, that the slope is 1. Well, given that information, or equipped with that information, I can give you a tangent vector. What's a tangent vector to what's the tangent direction to a curve where the slope is 1? Well, pick any vector where the two coordinates are equal. 1, 1, for example. We can call that capital T. It's not the unit tangent, I know, it's just tangent. And then how do I find a normal vector? So this is T. How do I find an N? Use that same trick that you learned a long time ago to find the perpendicular direction for a coordinate pair. Just switch the coefficients, switch the coordinates, and change the sign on one of them. That's normal. How do I know that's normal? Take the dot product. If you take the dot product of T and N there, you can see that it's 0, so they're clearly perpendicular. Do we believe that this is the correct answer? How do we verify this? Especially like all this implicit differentiation, which we haven't really seen up to this point. Let's jump over to GeoGebra and ask GeoGebra to plot this curve. And this is going to be a 2D problem, so we'll just work in the 2D calculator. We'll jump over to GeoGebra and ask it to plot this curve just implicitly. So 2x cubed minus x squared y squared equals 3 times x minus y minus 7. So there's that curve. Where's the point that we're interested in? Where's the point 1, -2? Well, we can ask GeoGebra to identify that for us too. There's that point. Does it look like the tangent, the slope of the curve at this point is 1? It does to me. Let's put a vector there. So we'll build a vector. And we'll tell it to start at A, and we'll tell it to go from A out to the point 1, 1, like that. And that certainly looks like it's pointing tangent. And if you want, we can get our normal vector. Let's go, again, we'll start a vector here, and we'll put its tail at A, and we'll move it in the normal direction, like that. And that's the normal vector. Still haven't really worked with tangent planes yet, but just kind of dredging up some old ideas about tangency and implicit differentiation. All right, in problem 176, we want to find the equation of the tangent plane to the surface at the indicated point, the very straightforward exercise and new information that we've learned in this section. So we have this function. Now, they've kind of done it to us again. Z is buried inside this equation as z squared. You have two choices here. You can either start computing these partial derivatives implicitly, which is a completely legit thing to do, or you can solve for z and set it equal to some function f of xy. If we solve for z, we get a slightly complicated situation. Z is equal to plus or minus the square root of x squared plus 4y squared. And you're immediately asked, well, which is it? Is it plus or is it minus? Well, how do we answer that question? Let's look at the point that we're interested in. Both of these functions are on the surface, define the surface that this thing defines implicitly. Which one do we want to pick in order to answer this question? We want to pick the one that the point lies on, 3, 2, 5. And if we plug 3, 2 into this expression, so we want to choose, these are called branches, the positive branch and the negative branch. We want to choose the branch that the point lies on. So we plug in z equals plus or minus 3 squared, 9, plus 4y squared, 16, square root. That's equal to plus or minus 5. What's the z-coordinate? In our case, it's 5. So we're going to get rid of that, and we're going to use the positive branch. The positive branch is the 1. All right. So now that we've settled on that, we know that z is equal to f of xy is equal to the square root of x squared plus 4y squared, square root. To find the tangent plane, we compute the various quantities. So first we'll compute the partial of f with respect to x, 1/2 x squared plus 4y squared to the minus 1/2 times, don't forget the chain rule, 2x. That simplifies to, this 2 cancels with this 1/2, x over the square root of x squared plus 4y squared. And it's not a great leap to imagine that the partial with respect to y is simply 4 over the square root of x squared plus 4y squared, like that. Now, we don't want these general partial derivatives. We want the tangent at the point 3, 2. So we want x naught equal 3, y naught equal 2. F of x of 3 and 2 is, let's look at it. Over here, it's going to be 3 over 5. And f sub y of 3 and 2 is going to be 2. I'm sorry, got a little bit of a mistake here. This partial derivative is for y. And when I plug in 2, 3, when I plug in 2 for y, I get 8/5. So now we've got the values of the partials at the point of interest. Don't forget we also need f at the point of interest. What is it, 3, 2? 3, 2. F at the point of interest is simply 5. And now we're ready for the plane. The equation of the plane given by the formula is z equals 5 plus 3/5 x minus 3 plus 8/5 y minus 2. That's the equation of the tangent plane. I don't know if you're getting tired of these visualizations. I kind of never get tired of them, but let's jump over to GeoGebra and just confirm our work. So we'll plot this surface and we'll plot this plane and see if they do indeed associate in the way that we would hope. So the equation up here, x squared plus 4y squared, equals z squared. Oops, I am in the wrong calculator. I want the 3D calculator. go. X squared plus 4y squared, 4y squared equals z squared. This is an elliptic cone. Let's grab the equation of the tangent plane. Z equals 5 plus, is it 3/5? X minus 3 plus 8/5 y minus 2. There we go. There's the plane. Definitely looks like it's tangent to something here. Let's put the point on there. So the point is going to be 3, 2, and 5. And there it is, sitting on the surface. I could probably scale this down a little bit. There it is, sitting on the surface. And this plane is just touching it there. So it looks like it holds water. Let's keep going. Okay, in problem 180, we're supposed to do the same thing. We're supposed to find the equation of the tangent plane at the point 3, 4. I'm going to assume that you guys can kind of figure that out, and what I want to do instead is I'll give you the tangent plane, and I want to talk about this idea of using the tangent plane to approximate the surface near the point of tangency. So if you go through the steps of computing the tangent plane, you should end up, and here's a way, I can give you the answer here and you can practice finding tangent planes. You should end up with something that looks like this, the natural log of 5 plus 3/25 times x minus 3 plus 4/25 times y minus 4. And what I want to do now is move over to Sage, and we'll just put these two functions into Sage, and we'll compare their values for points that are near 3, 4. Looking at Sage, just to remind everyone, creating functions in Sage is pretty easy. For example, the original function I think was called h. So let's define a function h of x and y equal to the natural log of the square root of x squared plus y squared, like this. And for example, if we plug in, say, x equals 1 and y equals 0, like this, that's going to be the square root of 1 plus 0, so the square root of 1 is 1, the natural log of 1 is 0, so we should get 0 out of this if things are functioning properly, and they are. All right, so we've got that function loaded. Let's let's define a function called p for plane, and this is going to be the equation of the tangent plane. The natural log of 5 plus 3/25 times x minus 3 plus 4/25 times y minus 4. And let's just double check that. If we plug in, say, x equals 3 and y equals 4, we should get the natural log of 5. That looks like it's working. Okay, now what's the idea of a tangent plane approximating a surface? Because the tangent plane is so close to the surface at the point of tangency, we would expect that the values of the tangent plane and the surface to be close to each other at points near the point of tangency. Here the point of tangency, at least in the domain, is the point 3, 4. So why don't we compare the numerical values of h of, say, 3 and 5. 3 and 5 is kind of close to 3 and 4. And the numerical to the numerical value of the plane at 3, 5. So if we let this grind away a little bit, we get values that are quite close. And 1.76 in both cases. We could move a little bit further away, so let's have instead of 3, 4, let's do 4, 5 in both. And even that's not bad, 1.8 in both cases. So that's the idea about using tangent planes to approximate surfaces at the point of tangency or near the point of tangency. And just to double check, we would expect that the two, we would expect the two functions to actually agree perfectly at the point of tangency. So if we put 3, 4 in for both of these, we get perfect agreement. And that makes sense, right? That's by construction, because in fact, this leading term right here in the tangent plane is literally h of 3 and 4. Okay, for our final exercise, you're asked to find the parametric equations for the normal line to the surface at the indicated point. I'm going to do this in a way that's perhaps slightly different from the book. And again, this is just maybe to foreshadow and also remind you of implicit differentiation. So in problem 184, we again see that the z is kind of buried inside this equation. So we have three variables, but we don't have a convenient way of solving for z in terms of x and y, because we have a z squared here and a z. So how can we compute the normal direction of this surface at this point 1, 1, 1? Well, what we're going to do is we're going to find the equation of the tangent line using, sorry, not the tangent line, of the tangent plane, using implicit differentiation to find f sub x and f sub y in the formula for the tangent plane. Okay, what is this f sub x and f sub y? So we're going to define z to be a function of x and y. This does a couple of things. This tells me that z is the dependent variable, and these are the independent variables. And furthermore, this tells us how we can differentiate with respect to x and y. So we can find f sub x by differentiating both sides of the equation with respect to x. But remember, as you do this, that z is secretly a function of x. All right, let's begin. Differentiating the left-hand side, we see x squared. The derivative of x squared with respect to x is just 2x. Minus, now we have 8 times x times y, and we're differentiating with respect to x. The 8 and the y in that context are constant, so we're going to pull them out. And what's left behind are x, which is of course a function of x, and z, which is secretly a function of x. And we'll do the product rule. We'll do the first times the derivative of the second, x, times the derivative of z with respect to x, which we're going to just, for our purposes, call f sub x, plus the second times the derivative of the first, and that's, we'll call it z. Okay? That takes care of the 8xyz term. Let's look at y squared. We're differentiating y squared, an independent variable, with respect to x, we get 0. And then last, we get 12z f sub x. What's f sub x? It's the derivative of z with respect to x. On the right-hand side, we have 0, and the derivative of 0 with respect to x is 0. Now, our goal is to figure out f sub x at the point 1, 1, 1. So we're going to replace all of these variables, x, y, and z, with just 1, 1, 1. So we get 2 times 1 minus 8 times 1 times the quantity 1 times f sub x plus 1 plus 0, we don't need the 0, plus 12, everything is 1, f sub x equals 0. Great. All right, we want to figure out what f sub x is, so we have 2 minus 8 times f sub x plus 1 plus 12 f sub x equals 0. On the left-hand side here, we have 12 f sub x minus 8 f sub x, so that's going to be 4 f sub x. And on the right-hand side, we have the 2, and we have the minus 8, which nets out to minus 6. We move that over to the right-hand side, and we get 6. We solve for f sub x, and we get 3 halves. 3 halves is 6/4 in reduced form. And then we repeat this process. So this is cool. We figured out what f sub x is for the purposes of building this tangent plane. Let's find f sub y. So that means taking this equation up here, x squared minus 8xyz, etc., and differentiating with respect to y now. So the derivative of x squared with respect to y is, of course, 0. Minus 8x, because in the context of differentiating with respect to y, both 8 and x are constants, and we have the yz that we need to differentiate using the product rule. We have y times f sub y plus 1 times z. So that's the product rule on the product yz. The derivative of y squared with respect to y is 2y. And then last, we have the derivative of 6z squared with respect to y. That's 12z times f sub y equals 0. And again, we're going to do the same thing. We're going to solve for f of f sub y when x and y and z are all 1. So what we get is 8 times 1 times the quantity 1 f sub y plus 1 plus 2 times 1 plus 12 times 1 f sub y equals 0. Let's clean this up a little bit. We get, let's see, minus 8 f sub y, and distribute that minus 8 onto the 1, another minus 8, plus 2 plus 12 f sub y equals 0. We have 12 minus 8 f sub y, so 4 f sub y, and we have negative 6, which we move over to the right-hand side. F sub y equals 3 halves. Again, let me just double check here before I carry on. 3 halves and 3 halves. Yeah, that's consistent with my notes. Great. Okay, we have f sub x and f sub y both equal to 3 halves. We also have to figure out what f of 1, 1 is. No, we don't. We already know what f sub 1, 1 is. F sub 1, 1 is 1. All right, so we'll note that down here. F sub 1, 1 is equal to 1. All right, so now what? The equation of the plane. Z equals f sub 1, 1, which is 1, plus f sub x, which is 3 halves, times x minus 1, plus 3 halves, times y minus 1. All right, why did I go through all of this? Simply to figure out what the normal vector is to the surface at this point. I can figure out the normal vector by figuring out the normal vector to this tangent plane. The normal vector to the tangent plane is the normal vector to the surface at the point of tangency. And remember what we're being asked. It's been a while here, but we're to find the parametric equations for the normal line to the surface. So we need the direction of the normal line. That's going to be the same as the direction of the tangent plane. All right, just move all of the variables to the left-hand side. So we get minus 3 halves x minus 1, minus 3 halves y minus 1, and z equals 1. Why did I do that? Because I know that the coefficients of x, y, and z are the normal vector. So minus 3 halves, and 1. That's the normal vector. Now that we have a normal vector, we need a point for the line to travel through, and we have that. The point that the line is traveling through is 1, 1, 1, and we're ready to write the equation of the line. The parametric form of the line is 1, 1, 1 plus t times negative 3 halves, and 1, just like that. This is the equation of the normal line. If you were to plot this surface, you would see this normal line sort of emerging perpendicular to the surface at this point. Okay, just to wrap up here, the suggested exercises, again, are limited. They exclude any exercises having to do with differentiation in the multivariable sense. So it's mostly just about planes, tangent planes, etc. So 163 to 187. When you feel comfortable with these ideas, go over to WebWork and try the assessment for Chapter 4, Section 4. Thanks a lot.